Good evening, everybody. Welcome back. My name is Kevin, and welcome to the ESP32 product creation journey. Before we get started today, I want to give a huge thank you to everybody that's followed in the last week or so. It's great to see all the new people joining in and checking out what's going on here. Happy to have everybody, and I apologize also for missing last night. I said I was going to stream last night. People have been asking for a schedule. I tried to give one, and then I bailed on it because it had been a super long day and I was not feeling well. It would have been a waste of a stream because my brain was mush. And so hopefully that's not going to happen today. So today I want to talk about a little bit of we're still kind of on a bit of a tangent from the core thing that we're building, which is an ESP32 based consumer product, but also a development board. I'll post the code when we get to a point where it's good enough to post. Oh, Rogue Security, thanks for joining. Great. Much better today. Thank you for asking. I'll open source the code that we're building up here that's sort of a base for everybody, and I'll talk more about that here in a little bit. But I'm also looking to build a consumer product out of this that is basically, for those that are maybe new to the journey, I made this product. It is a hockey puck. It's a real hockey puck. Huge Washington Capitals fan, that has an e-paper display in it that shows the team's record, their points, their division rank, and kind of a streak they're on, when the result of their last game, and when their next game is going to be played. And I'm taking all of that and we're going to put it into a puck holder design. Let's get the front of it here. Looks like that. So anyway, that's what I'm building, but the guts of this, based on an ESP32, should be applicable to anybody. And what we've been going through the last several episodes is sort of my own personal learning curve, and hopefully it's been instructive to others, of writing code in ESP-IDF. Now, you'll probably see most code examples for ESP32 online using the Arduino framework that they've built for ESP32. I'm not doing that. We're writing all of this straight C++ with the IDF, because that's how I prefer to do it. I was thinking about like giving a reason why I'm doing that. I've never considered, and there's probably arguments to counter this, but I don't consider the Arduino stuff production ready. There's a little bit too much black box going on. I prefer to write the code so that I know all of the raw things that are happening. We're still relying, obviously, on the IDF framework, but I prefer to do it this way, but that's me. If you would like to approach it a different way, that's great. To each their own. But for us, we're building all of this in the raw IDF framework stuff, and like I said, I'll open source the meat of it when we get to a point that it's ready for that. It's not yet. But first thing I want to talk about today is threads versus tasks. Now, a couple of, I think it was the last stream, I haven't posted it to YouTube yet, but the last stream, for those that caught it on Twitch, I showed the difference between C and C++, and how for some features of C++, specifically string stream, which we used in the last stream, is a huge cost in Flash code size. So we almost doubled our Flash. We went from like 200 to like 399K, if I remember, just by using one line of code of using the standard string stream. And so while a lot of things in C++ work, the compiler supports it, got to be mindful of your code need, like your Flash size needs. And if it doesn't matter and you've got plenty of room, by all means, use those features. In our case, we can't afford a 200K hit just from using something like string stream. So the other thing that I wanted to explore around that is this idea of threads versus tasks in IDF. Now, under the covers, it's all FreeRTOS tasks, but they've built an abstraction layer so that you can use the C++ threading standard thread syntax, which, again, I like for portability reasons, and also because it decouples me it doesn't decouple me from the underlying implementation, which is FreeRTOS, but my code is just using standard thread. So it decouples me in that regard to where I can port this to other chips if we need to in the future. So I wanted to explore the cost of that, and I found out that the cost is actually not very high. When I did and I don't think I'm gonna go through it again. I'm gonna show you how to do threads, but I won't show the difference between task and thread. But I found that just in a raw, like do it with the task and then swap out the code and use thread instead, it was about a 10K flash difference, which is not insignificant, but it was small enough that I'm going to take that hit, and the difference in code is small enough that if I ever need to regain that, I can always switch it back, if that makes sense. So let me show you what we had to do to get that working. First of all, in our main cmakelist.txt, pro tip, again, if you're not in the Discord, Eager from Espressif is in there dropping huge knowledge. Great resource to have there. But one of the things that he pointed out to make one of the things I struggled with and was probably painful for people to watch, or maybe 4 or 5 episodes ago, was it was saying it couldn't find a header file, and that's because when you do your IDF component register, you specify your sources, which in this case is just main.cpp, and then we have this private requires of, I'm including, this is my component serial logger, but then we needed to include NVS flash, Wi-Fi provisioning, and for threads to work, pthread. However, Eager pointed out, I guess if you just don't include anything there, by default, it will include all, the compiler will look through all available components in IDF. And so that's sort of and he pointed out, don't do that for a production build, but just for, a quick project or debugging or whatever, if you remove all of those, it will look in the full global scope of components. Whereas if you start specifying them, it's only going to look for those. And so if you haven't included components that you need, you're going to get like a missing header file during compilation. Sparky, what's up? Great to have you. And thanks everybody for putting time zones in. We've got time zones, sounds like US here where I'm at, and then many hours ahead, halfway around the world. And so it's great. Evenings is probably when I'm going to do this, because it's, getting to be late at night where I'm at, but I think it's early morning in other parts of the world. So great to have everybody watching from all over. Okay, so to get threads working, I needed to add this pthread. So it's another component that you have to add. Otherwise, you're going to put the include statements in, and it's not going to be able to find it. So in the CMake lists, we have to add pthread. So that's the first step to enable the standard thread syntax. And then over here in main, we have to include it. And so where did we have to include a couple things. First of all, we have to include thread. That's just this is standard C++ stuff, include thread. And then this ESP thread, ESP_pthread.h is a companion helper library for us to still do xTaskCreate type things with the standard thread syntax. And you'll see what that means here in just a second. The code right now is a hot mess of me messing around and getting ready to move us forward in the project code that we're trying to write, which deals with provisioning and stuff. We're going to talk about that a little bit later in today's stream. So we've included the files. You can see here, this was me playing around with it. Ignore the code in here for now. When I started, it was just this log manager info, but you'll notice that the syntax is, the signature is a little different. So if you're going to use thread instead of tasks, you're going to say void pthread task, and then you pass it nothing. Now, you can pass it arguments, which I'm not going to cover today, but remember, this is just straight up, if you go and look for the standard documentation of thread, you should be able to call it just like that. In this case, I'm not accepting any parameters, so it's just void pthread task and then void argument. Whereas when you do xTaskCreate, which I believe I removed all of them, xTaskCreate, if you remember, would look a little different. You would change it to be void params, like that. By which you don't have to pass an argument to an xTaskCreate task, but the signature needs to look like that. So just FYI. So that's it. And then in here, it's just like task. You normally will have a while loop that will go forever if it needs to run forever. You don't have to always run tasks forever. It could be you just spawn off a thread to like accomplish something and then shut down, which in fact is how our provisioning will eventually work. Like it's not going to run forever. Once the device is provisioned and connected to Wi-Fi, that task on that thread will just be done, and it will release the resources back to FreeRTOS. So this is the form that you would write your function in. And again, you just write whatever you want in here. And then there's this little helper function that they put in the examples, the pthread examples. And this is where we can get some of that xTaskCreate like functionality, where we can say, what is the thread name? What core do we want to pin it to? What the stack size is, and then the priority. And so and this is a great little helper function. You just pass all those things in, and that will set the underlying implementation to use those values, because none of these things are specified through standard thread. So when you want to do standard thread, I'll show you how this looks. Okay, well actually, so I still have some code here. So I have, this would be like the FreeRTOS standard IDF way to create a task. And I wrote this report heap memory, which I'll show you in a second. It's pretty fun. You would do xTaskCreate, and you give it the function, which is the task. You give it a name, which is memory. You give it a stack size. The null is any arguments that you want to send to it. In this case, none. You give it a priority, and then this is an output variable where you can get the handle back so that you can do operations on the task that's running. So that is how the standard way to do it. And right below it, as you can see, so let's comment that out. This is the standard C++ thread way to do it. You just say standard thread, give it a name, in this case, any core, and that's an artifact of the examples. And then you pass it the function, the end. That's it. Now it's running. One thing that you need to remember to do is if you're going to do standard threads like this and you're not going to have anything looping in your main, I moved it all the way down because I'm messing with provisioning. You have to do this down here. This any core, which is just the name of the thread. Let's rename this. Let's not be silly. Let's rename any core to be memory thread. Okay. You have to call join, and what join does is it says, I'm going to wait until the thread expires. Otherwise, you're going to return from app main, and it's going to mess everything up. So this is sort of if you're not going to have something like this last line down here, I'm going to make this a little bigger so everybody can see. If you're not going to have this like while true, just looping on this main app main function, which is unnecessary. Like this does nothing. There's no sense in having that line of code. If you just join the thread, and again, you can look this up in standard C++ documentation. This is saying, hey, wait until that thread exits. Since the thread is an infinite while loop, it will never exit, and so everything runs as you would expect. So I'm going to see if I can get this to run with all of this code commented out and all over the place. So that was how you launch, without any arguments, a basic thread that performs like a task. But you notice we don't send any of these things like the name or the stack size or any arguments or the priority. So what's the behavior in this scenario? Well, it's actually defaulted, and we can look that up. If we do, let's get our environment set up here. ESP-IDF. Okay, let's do idf.py menu config. And it's in component config. And it is, I always blow over it, I feel like. There's a thread one. Pthreads, right here. Okay. All right, and here is what everything is going to initialize with if you don't specify. It's going to have a default task priority of 5. The default task stack size is going to be 3072. And then the default name is going to be pthread. And so if we look back up at the code, instead of memory like we have right here, it'll be pthread. Instead of 4096, it'll be 3072. And then the priority, instead of being the idle priority, it'll be 5. And so you can change those defaults if you want. However, you probably don't want to create everything with the default. And so that's where we'll go ahead and exit out of this. That is where we can use this little helper function. And again, this helper function, which, where to go? Right here. Straight from the example code, but it's very simple. Again, it just creates an ESP pthread config type that we can then set. And so if we come back down here, we can say, let me just uncomment all this code so you can see it. We could say, give me a thread config, and then we just say create config, and then it's like, this is the name. I said receiver. You can set the core, which I set to no affinity, which means it will run on either core 1 or 2. The stack size, 2048, and then you can give it a priority. And then once you have that, you call this ESP pthread set config, and you pass it that config. And now, from that point, it changes that underlying implementation to have those defaults instead. And now you can just do the standard C++ thread calls again. Standard thread, I called it T2, thread 2. It's not Terminator. And pass it, again, just the tasks that you want to run over and over. Now, so that makes sense. And then if you want it to be something different, you just create a different config, create a different. Now, if I were to do another standard thread T3, it would inherit the same settings that are set right here. It would have the same name, the same stack size, and all of that. And so that is how you do threads in IDF, which is pretty cool. One thing I was playing with was how to communicate between threads. Now, IDF has some different things built into it, and one of them is used in the provisioning sample code, this X event group wait bits. You can set bits in different tasks and then wait for all of the bits to be set. Like it's a free RTOS. I shouldn't say IDF. I believe it's a free RTOS concept of how you can send messages between tasks and things like that. But again, in the interest of portability and reuse, I want to try and not do the raw free RTOS things as much as possible. I want to use the C or C++ standard ways of doing that. Again, see previous episode where it makes sense with Flash code size. And so one of the things I was messing with, I'm going to show you these. I'll see if I can get all of these working. It's going to be a struggle because I don't need to do any of that. Okay, we're going to get rid of that thread. That was me messing with storing things in Flash. We probably don't need to init Flash either. This is never going to work. Okay, so I'll have just report heap memory and pthread task running. And let me show you those. I can't remember if I've shown you this report heap memory. But what we're doing here is, I won't show you all the code. It's not super interesting. It prints out like a top-like Linux command of like, here are the tasks that are running. Here's their CPU usage, the name, what core it's running on, and how much stack, the high watermark of the stack, which is actually how close you came to running out, which the closer to 0, the closer you're coming to a stack overflow. And what I wanted to mess with was, how do I communicate between threads? And again, not thinking in free RTOS terms, but thinking like if I were writing a C++ program, how would I communicate between threads? I have done some multi-threaded C++ programming, but not a ton. And so one of the things I was messing with was using a queue, just like a standard queue. And I actually found out, again, I'm testing the flash size on all these things. You can see I've included queue up here. Queue is very light, surprisingly light on flash. And so I was using that when I got the memory. Where do I do that? Oh, right here. Once I printed out all the memory, I'm doing a message queue, which is just I've declared up above, which is a queue, and I push the heap info largest free block. So that's the largest amount of memory that I could malloc at any given time. And in my pthread task, this is again running on another thread. It's just looping forever. It's just saying, if there's something in the queue, let's pull it off the queue and print it out. Now, this is not a practical or useful thing at all. This is literally me just messing around. And so this was me saying, hey, like grab the front of the queue, print it out, and then pop that message off the queue. But you get the idea how you could use this to send messages between threads by pushing things onto a queue and then having other tasks look at that queue and pull them off. More on that in just a few minutes. This is going to be two parts. We're going to talk about threading, and then we're going to switch gears altogether in overall design of what we're trying to build. Okay, the last thing that I would highly recommend, and it's one of my favorite things that I've learned in the past year with C++, is standard chrono. And this is one of the things I love about using the standard library. So if we look at, let's come all the way down here. If we want to delay in a task, this is the format that we use. We use this like vtask delay 3000 divided by port tick period milliseconds, and that gives us a 3-second delay. In the threading example, as you can see, I'm using standard this thread, which means the thread that I'm running on, sleep 4. This is all standard. I didn't write any, this is not a function I wrote. This is just standard library stuff. And then I can say standard chrono seconds, 1. So do this every 1 second. And you can do this for anything. There's a standard chrono seconds, minutes. I believe there's also hours. You can create your own standard chrono types. And they're all interchangeable. You can do a lot of really cool time comparison, adding and subtracting if you're using the standard chrono times. And so this to me reads so much better than like, task delay or V delay, 3000 divided by some random variable. Like this is like butter. I love this. This thread, sleep 4, 1 second. Like it's beautiful. Anyway, personal preference. I love it. And again, the cost of this is one of those very close to zero cost abstractions. Like this thing is super, super light in terms of flash. And I just think it reads so much better. So let me just show you how it works. I can't remember, for those watching, if I've shown you this before, just say we've seen it. Don't bother. Let's see if it'll build first. There's no way. Fingers crossed. It built. Man, I love it when it builds. It's so good. Okay. The reason I wrote this little memory reporting thread thing is because I wanted to keep an eye on memory and specifically stack size and CPU usage as I write different parts of this code. I want to be able to turn this on. And I think I'm going to make it a component that I can include and turn on and off just for debugging. This would never run in production code, but it's fascinating to see. And you'll see right here, there's not a whole lot, but it's going to keep updating and updating and updating. So I'm going to just copy this out. I'm going to try to copy it out. You got to be quick or else another one comes in. Control-C. Okay, I think I got it. Okay, so I'm going to erase this top line. This is my logger. It is printing out this like it's debug. This is the time, and the tag I gave it was top because it's like the top Linux command. And you can see it's got the name, stack, CPU, and core. And I didn't put enough equal signs there to cover core. But I wrote this so that like if it's no affinity, meaning it can run on either core, it's this little tilde. I feel like I remember saying this before, but you can see every task that's running. This is how close, the closer to 0 this number is, the closer you came to a Stack Overflow. And then the current CPU usage in percentage. So like right now, after getting started, you can see the idle tasks on both cores, 0 and 1, are running most of the time. But for the purpose of our threads, you can see that the first one I created, it just gave it that standard default name of pthread. And then the second one, when I said receiver, when I used that, like set the settings for it, you can see that there. And so just a really cool thing. And then I print out the free heap bytes and then the largest free block. And then remember, after I print out the largest free block in this thread right here, I pushed it on the queue. And then this is that other thread pulling it off the queue and saying, hey, I got some heap info. It's this 129,588. You can see it just matches that. Again, no practical value. That was me just messing around. So what's really cool though is when I was doing some of the Bluetooth provisioning stuff that I have commented out right now, you can see all of the different tasks that are running for Wi-Fi, Bluetooth provisioning, and all that stuff. And you can kind of see like which ones are using CPU, how their stack sizes look. And this can also be used for like tuning stack size as well. So like this P thread, you can see I have a massive extra amount of stacks here that I could remove. So when I create the stack, I can make it much smaller. Like in the receiver case, I changed it to 2048 instead of that default 3072. And you can see this is lower towards 0. You don't want to over-tune it. And this is a point Eager pointed out. Like, don't worry about fine-tuning that until you've written more code and you actually start to run out of space and things like that. You can start to fine-tune it. And I agree with that approach. But this gives me a tool as we're writing code that I can turn on and say, how are things looking? And is anything hogging the CPU and what core is it running on and things like that. So anyway, that's it. That's my thread section of this. Hopefully, again, I like the thread syntax better than the FreeRTOS task syntax. Personal preference, but that hopefully shows you how to accomplish that and use it in your own projects. Now, let's move to part 2 of this. As we're writing all of this code, I realized, again, I'm trying to build an e-paper display product. I'm going to unplug this. I've got, some people have pointed out they want to build projects that they connect to their soldering stations, and people have shared some really cool ideas that are completely different than what I'm working on. But the main like shell of all of this is the same. And I want to show you, this is something that I built. It doesn't look like much, but this took me a lot of trial and error to put together to create a smoothly working provisioning approach on the old hardware, which is a particle P1. It didn't have the features and the power that the ESP32 have, but this flow is really helpful. And I did all of this with a state machine, and I created these different states. Like I've got this pre-configured state, this shell state, this will go away completely, and this configured state. And the reason for this is because the device needs to do different things based on the state that it's in. And something that we're going to have to solve is what is the best way to create that flow when all of this stuff is going to be running in tasks or threads, which is, I think, the approach we're going to take. But we still need to have an overarching framework that's directing all of these pieces. And so I'm going to just walk through this quickly because one of the things that even the examples with provisioning lacks is, and I talked about this in a previous episode, is when you enter the wrong credentials currently. Yes, Rogue's Cheered, I will zoom. I'll zoom in just a second. When you put in the wrong credentials when you're provisioning, it takes them. The ESP32 will say, I'm provisioned because I have credentials. Like I have a Wi-Fi SSID and I have a password. Even though it's wrong, it'll say I'm provisioned, but I can't connect to Wi-Fi. And the app will even tell you, like, please factory reset your device. Well, that is not a realistic, well, I'm sorry, it is. I mean, you could do it that way. I think it's a crappy user experience to say like, oh, I couldn't connect to the Wi-Fi. Sorry, like, I don't know, reset the whole device and try again. Like that's not super helpful. And as we've pointed out, I don't have a button. So like I don't have an easy way for people to factory reset, which we'll talk more about later. So let's zoom in here. Is it Control Plus? Yeah, there we go. There we go. Oh no, don't move things around. Okay. So when we first come in, I do the state machine start. I say like, do I have credentials stored for the Wi-Fi. And that's all I need to know, because unlike ESP32's is provisioned, once I am provisioned on the old hardware, I know we're good to go. And so I say if yes, I come straight down and go into the configured state, which we'll come to in a minute. But if I don't have credentials stored, I go into the pre-configured state, and then in my case, I say, am I connected to power? Because my device is battery powered. If it's not connected to power, I'm not going to try and provision it because that uses a lot of battery. And I put that in my instructions, like it needs to be plugged in when you're setting it up. So if I say no, I show my setup screen, which I have. Just a second. I show this. Let's get the glare off. There we go. It says get started, and it gives a little bit.ly link for people to go to, which links to my documentation. I show that, and then I say sleep until plugged in. And so I have an interrupt, and I'll do that on this firmware as well. I'll have an interrupt that when you plug it into power will wake the device up. And so that's how we do that. If I am connected to power, then I go into this configuring state in the state machine. And then I check again, am I connected to power? So if somebody has unplugged it, then I go back to showing the setup screen and exit out. This has serial connection will not apply nowadays because I can run a serial shell on a separate thread in ESP32. That was not something I could easily do on the P1. So we'll ignore that. And then I'll say nope. And then again, I'll say, does it have credentials? I don't remember why I do that again because I think we would have taken care of that here. Anyway, doesn't matter. I'm going to turn the Wi-Fi on, and then I'm going to wait. Is the Wi-Fi ready? No, something went wrong. Clear the credentials, go back into the configuring state. So at every point here, I'm going to try and fix the issue so that the customer doesn't have to do some weird process. I try and automatically recover from things. So turn on the Wi-Fi. Did it turn on and is it ready? And we can check those things with some function calls. No, clear everything, start over. All right, it is ready, great. And this Wi-Fi ready is really our provisioning process to where we get credentials. And then I have a little test in here. Ping the internet, try and reach outside. Just because you connect to an AP, even if they've put in their right credentials, I wanna make sure right out of the gate, if they can't get to the internet, something's wrong. Now, I understand they could choose to provision their device while their internet is down or having a service disruption, and this will be, I'll clear out the credentials and go back into configuring. That, to me, is an edge case that I'm not worried too much about. I've gotten 0 complaints about that. Ping the internet. Did that succeed? No. If it didn't, automatically wipe the things. Don't show a message that's like, sorry, I don't know what happened, reset your device. Just clear the credentials for them because something went wrong. And then go back into the configuring state. And then, again, at any point, if they just unplug it, reset the screen to set up and go back to sleep. If it does pass, now we go down into the configured state. Now, this entire block is applicable to any project that wants to be battery powered and use the ESP32 and provision itself. Like this general flow, I think, is the best way to do this to make sure credentials get stored. Okay, that brings us down into the configured state. Again, turn on the Wi-Fi if it's not already on. This Wi-Fi ready, yes or no. The Wi-Fi ready here is like, are we connected to the AP and do we have an IP address is really what that is. And then if yes, I just put update display. That's what my product does. But like this is really the box, the only box out of this entire flow that would be replaced with enter whatever you're working on here. And so this is what I mean by like this whole shell, I think, is helpful to anybody else that's doing ESP32 based projects or products, because all of this stuff about like provisioning and getting it connected to Wi-Fi is the same. There's no sense in reinventing the wheel for that. And then just insert like your core application basically right here. And then I do some other things out here of like, is it connected to power? After I update, is it connected to power? No, which it normally won't be because it's battery powered. Go back to sleep. If it is, I have this connect to particle cloud. We'll do some things around this as well with provisioning, not provisioning, my apologies. with OTA updates. Like this is the point where I would try and do an OTA update. Again, if you have buttons on your device, you could use like a button press or something else. Because it is buttonless, I have to automate all that. And so I want to make sure that the core function happens, which is updating that display with what people want to see. And then if it does that, and it's connected to power, because again, this is a huge power drain, try and do an OTA update if one is necessary. And we'll get to all of that in future streams where we get all of that to work. And so as part of this, I've started, I think this is it. Okay. One of the things I find helpful that we don't spend a lot of time on as developers is this. And you can see this is my log manager, iLog handler, ESP serial logger that we've made for that logging that we created, that abstraction of logging. And this is really helpful because something that I found, and this is a piece of advice that I would give anybody that's, whether you're a seasoned developer or if you're just getting started, this is a step that seems like a waste of time because it's so easy to take these and to start pounding on the keyboard and getting code. And it's like a drug, like it's addicting because you get something to work and then you get a little bit more to work and then you start tweaking it. And what you end up with 10 hours later is a giant mess. And that works. I mean, that's the thing is it normally works, but when having read one of my favorite books about architecture, clean architecture, I believe is the name of it. When you break things out and you can look at them in a high level block format like this, you can decide like, where do I want to implement certain pieces of functionality? How do I want things to relate to each other? You learn all these things if you've done computer science. You learn about all these best practices and inheritance and keeping private things private and only exposing public interfaces and stuff. And it kind of just, yeah. But having dealt with lots of different code bases, it's really helpful to break these things out and say like, see which way the interface arrows point, like what components need to know about other components and how much do they need to know, and creating as much of this separation as possible really when you're designing it at a high level on the the graph whiteboard here, I find very helpful. It's a step that a lot of people skip, and even I've skipped. You can see I've created the log stuff after the fact, but what I'm trying to do, and this is what you can see here, is like, what are all the different boxes that we're going to need? And so like, this is me just spitballing here. I've got like the main app, that's like updating the display, right? And then I talk about this config module, which I should rename provision let's do it. Why are we talking about it? Provisioning module. And we talked about this before. It could have a serial interface, it could have a BLE interface, it could have a cloud interface. No, that I did mean config. This is not provisioning. My apologies. This was for like setting, like configuring, like what kind of settings do you want to turn on or off? Again, if you don't have any switches or things, all the stuff you can store in Flash. And so at a high level, I'd want to talk about that as a config module. Like I would do operations. I would have a config module interface of like set value, get value, and it would have no idea. The main application code would call that. So it would be something like this. But underneath of that config module, you would draw, and again, I don't want to get too much into architecture, but these arrows would point this way, like the direction of the arrow matters. The main app would use the config module, but these would inherit from the config module. So you could swap them out. You could say, I want to do configuration through serial. Great. The main application doesn't need to know about that at all. You could implement it as a serial interface. You could implement it with the BLE stuff, or you could do like some cloud interface where people create their settings in a web interface and then it gets propagated down to your device. And so these are examples of some high level modules. Display module. In my case, I've got this e-paper display. An OTA module. How do you get updates? Power module. Am I connected to power? What's the voltage? Remember, we did all that stuff to design in reading voltage. Like, abstracting that away, and in the main app, it would be really tempting to say, like, if you remember from our design, we created that voltage divider. It connected to a certain pin on the ESP32. In our main app code, we could say, well, I know it's connected to IO pin 27, and so I can just use the IDF calls to configure the pin as an input and then read the voltage and do. You could, or you could create an interface that's a power module that you just from your main app say get battery voltage. And then the implementation of that is hidden away from the main app code so that if you change what pin you put it on, or maybe you're not using a voltage divider anymore, maybe you're using like a fuel gauge type chip that communicates over I2C, the main app shouldn't know anything about that. It should just know, hey, there's a power component that I can call get battery voltage from. And this really helps with reusability, portability, and decoupling of the code. And so the last thing I want to show, again, just like the sausage making of this process, is what I did is I went through that the overall graph of like the flow chart of like provisioning and getting the main app set up. And then I just started writing down, let's make this like main here. I just started writing down some high-level modules that will these will likely be a one-to-one match to IDF components, custom components that we will write so that our main code can just be talking in high-level interfaces to all of these things. And so we'll have a Wi-Fi module. And this is how this is how I do it. I'm not saying this is how everybody should do it, and you might have a different approach to this. This is just the way that I found over the years that helps me sort of start to design firmware, or any software for that matter, to solve problems, real-world problems. So in this Wi-Fi module, I'll have things like, and these will probably turn into function calls of some sort, but I need to know, are there Wi-Fi credentials stored on the device? And then there's a particle P1 way of doing that. There's an ESP32 way of doing that. There's an STM way of doing that. If we write this at a high enough level, the main code will all be portable across any chipset. And what you'll do is you'll just carve out the implementation detail. And in Arduino, you'd say pin mode to set an input or an output. On the ESP32, there's oh gosh, I can't remember there's several underscore line function call that you do that does the same thing. Those are implementation details. We don't expose those in the interfaces. We need to turn the Wi-Fi module on and off. So there's probably going to be like a on and off, or radio on, radio off. We need to initiate a connection to the AP. Now, some of this, what you'll find is some people will, and this is really hard not to do, you over-design. You think too much into the future of like, what could it maybe do down the road? The best way to start is just to say, what are the things that it needs to do now? And just start there as a base. Don't try to get too crazy of like, oh, maybe one day I want to do some crazy thing. Worry about that one day. Don't worry about it right now. And that's not to say that you need to lock yourself in, but again, don't overthink it up front. Am I connected to Wi-Fi? Does it have a connection to the internet? Again, this is just a simple thing that I'd want to abstract to like ping something like 8.8.8.8 to see if I get a response. And then clearing credentials. Again, this is really important. We don't want to have the user factory reset to get rid of their Wi-Fi credentials. That's not a great customer experience. And it also isn't helpful if they change their Wi-Fi password. Like, hey, I changed my Wi-Fi password. Great, factory reset your device. That doesn't make any sense. Okay. These are different events that we can push through the system. I've got this provisioning module, and this is, again, going through the code. Like, here are the different types of things that we'll probably have to do in a provisioning module, and here are the events that we might want to fire and read from other parts of the system. The power module, is the device connected to power? Like, is it plugged in? In that same module, I might want to handle the sleep. stuff like sleep for a specific amount of time, or maybe not. That might be its own separate thing, but right now I feel good lumping that in with power. Sleep until woken by an interrupt. I started thinking like we need some sort of settings module. This is if a user selects certain things, we'd want to save that. And then some sort of, this event handler was me starting to design around should these modules implement some sort of high level overarching event handling class where they're all an event handler, which they can process events. That's just something that I'm thinking about, and I don't know where we're going to head with that. Because again, I need a way to coordinate all of these things in the main application to say, to implement that flow chart that we showed a little bit ago. So again, these are just the things that I'm going through to try and design where we go from here. The next thing that we're going to work on is the Wi-Fi module and the provisioning module. And they're really munged together in the sample code. And let's look at it. It's all commented out, but bear with me here. There's a couple of things. We need to init NVS flash, and this is because we store Wi-Fi credentials in Flash, which I do want to show you this. Sorry, we're gonna build this. Let's do that. Where are we at? 46 minutes? We got time. Now it's gonna be a game of getting the code to compile when I've got like 4 different things happening. I think that's all we need to do. This is all the provisioning code. But let me show you what I meant so I'm not too scatterbrained here. Like in this provisioning example code, you can see like we have this net interface init, and then we have registering for event handlers. We're going to register for provisioning events, but we're also going to register for Wi-Fi events as well as IP events. These are 3 separate concepts in IDF. There's the provisioning module, there's the Wi-Fi module, and there's the TCP/IP module. And so these are all kind of run together in this code, and this is like a minimum amount of code to get the thing to work, which is great for an example, not great for a solid project or product. You'd want to separate these things out. And that's just, again, personally for me, for maintainability. Okay. And then I've talked about this before. We're going to do away with a lot of these ESP error checks. This is a macro that just says if it doesn't return ESP OK, reboot. Like stop everything and reboot. The problem with that is some of these cases we might want to not just reboot. Like for example, because I have a display in my product, if one of these things fails, I could, if I wanted to, print out some sort of code or error on the display, because the display should always work. It's just connected through SPI, so it doesn't rely on, some of the things that could break with Wi-Fi and connecting to the internet and stuff like that. So I don't want to just blow everything up and restart. I might want to say, hey, print error code like 123, and then if somebody reaches out, they could say, hey, I was trying to do it and my device says 123 now, like error code 123. And I can be like, oh, that's because the Wi-Fi provisioning manager init call failed. And that could be helpful to me. Anyway, we're going to get rid of some of these ESP error checks. So you can see, like I said, we're doing provisioning manager stuff here. And then where we get, there's a Wi-Fi call in here somewhere. Oh, this is the error handler. We'd have to be. So anyway, we're doing the Wi-Fi init STA station. Anyway, they're all very coupled together, and I think we could take this code and accomplish the same thing, but create a nice interface that we can reason about the code a little better. Not that this is hard to read. It's just, again, it's very script-like, just top to bottom, and a great example, but not what I want to do for our application. So I think that's everything to, this read NVM content. So one of the things, thank you again, Eager, for setting me in the right direction, was if you do a search for how do I reset the Wi-Fi credentials on an ESP32, you get a lot of different suggestions and forums. And a lot of that is, again, because people are just doing maker projects where it's like, oh, just use the flash erase, the IDF .py command, erase flash. Yes, that will get rid of the credentials. It also wipes out everything else on the chip. That's not what you want to do with a product. Another suggestion is we come down here into main. And this happens if you get an error, and I still need to research this more, but if something happens where the NVS partition gets corrupt, you can call NVS flash erase. NVS, again, is the default partition. You can create as many non-volatile storage partitions as you want, but this is the default one, where if we look at this OTA partition thing, you can see we've got NVS, which is a data partition. This is the size, in addition to our 3 code partitions, which again, we're going to change. We'll do that in another stream. But you could do NVS flash erase. Yes, that's also going to erase everything else that's in that NVS partition. And there are other things, but there wasn't a whole lot of information that I could find to say like what exactly is stored in those other partitions. And so I wrote a task that I called read NVM, non-volatile memory contents. And all it does, similar to my memory type task, is it goes through and I look at the NVS partition, and you can use these calls to do other partitions as well. And then I get an iterator. This is the iterator, sorry. And then I say, give me the entry info for it, and then give me the next one. And you can look up namespace versions or specific keys. But I just wanted to loop through like, tell me what's stored in NVS. And so then I print out the information, like what namespace is it in, what's key, and what type of data is stored at it. And it was pretty interesting. So let me show you that. Let's see if we can get it to compile again and see if it works. Flash monitor. And then we'll wrap up with this. I got a new toy sitting right here. I'd show it to you. It weighs way too much. My server came in. So I told everybody I was trying to build a home lab. I got the rack for 80 bucks, 42U. My Dell PowerEdge R610 is here, and I want to play with it a little bit tonight before I go to bed. So really excited. It's a monster. I love it. Did it build? No, it didn't. What's the problem? Oh, it's not, my thing's not plugged in here. Try that again. Okay. Okay, and here we go. It just prints out. I think it only does it once. Yeah, it does it one time. So it doesn't keep going. Look at all the stuff that's stored in the default NVS partition. And I'm just going to grab them all here and we'll put them on the big screen. And we'll shrink this down. So if you wanted to, you can see like the namespace, this nvs.net 8211 is where all of the Wi-Fi stuff is being stored. You can see there's quite a bit of things stored, but a couple of those things is you've got the station SSID and the station password, and the type is 42. What does that mean? Well, let's grab, maybe, come on, drag over here. Pop OS, you're killing me. Let's grab the system. No, let's go to networking. Let's go into Wi-Fi. And to cheat, I'm just going to look for hex 42. What do you mean? Oh, not Wi-Fi. What am I talking about? Storage. And let's look at non-volatile storage. And let's look for 42. Okay. These are all of the different types that you can store in non-volatile storage. You can see they just have hex things. And so type 42 is a blob type. There's also string types, 64-bit integer, 32-bit, all the way down here to unsigned int 8. And so we can see that both the SSID and password are stored as blobs. And there's limitations on how long a string can be and such, but I thought it was really interesting to see, like, look at all this stuff that is stored. And so what else are we getting rid of? So yes, if you clear the whole NVS partition, you're going to wipe out all the Wi-Fi stuff. But look what else you're going to get rid of. And this may be important. In fact, it may be crucial to your application. The calibration data for the ADC is stored there. So if you have done some, like if your device uses the onboard ADC and you have done like what you would call a factory calibration and you've stored that data in here, well, if you wipe the whole partition, that data is gone. And so I just wanted to have an idea of what all else was stored. Not much else. It's mostly Wi-Fi information. But another thing that we could do, and one of the forums suggested this, I don't like it, and I'll explain why in a second, is now that we know, oh, hey, if we just look in the namespace this and the key this sta.ssid and sta.password, we could very surgically just remove the SSID and password. The reason I don't like that, and a community member pointed this out in the thread, was this, to me, is an IDF implementation detail that we don't know about. Like, there is no place in our code for provisioning that we set this. This is set by the provisioning library. And so if Espressif decides they want to start calling this station to be more explicit .ssid, and your firmware relies on sta.ssid, once you pull that update, and you should find this through testing, so this is kind of a contrived example, your code's broken because you relied on an implementation detail from IDF. And so I don't like the idea of surgically saying, oh, I figured out because I was clever what the keys are, and then I'll just hand delete those. I didn't want to do that. And so there is an actual call. It's ESP_Wi-Fi_reset, I believe, which will come in and it will clear all this stuff for you. And now that you're using the Wi-Fi interface function, they could change it to whatever they want. You'll be okay because you're using the layer of abstraction that's above it. So anyway, lots of cool stuff. Like, I've been learning a ton about non-volatile storage and Wi-Fi and provisioning. And I mean, I was shocked at how much stuff is stored in here just for Wi-Fi. And again, all of these are manipulated through different calls. But again, if you want to get super hardcore, you can really hand tweak some of this stuff. Don't recommend that. Again, use the abstraction in the interface that they've provided for you. Okay. I think that's going to do it. I think we covered, I mean, we were all over the place there, but those were all the things that I wanted to catch everybody up on. Next up, what are we going to do next? What I'm working on is, again, taking all of this provisioning code, breaking it out into the different modules so that we can reassemble it in what I feel will be more maintainable and easy to reason about code. So it's not just an example run straight through. Again, it's excellent for an example. It works and does what you would expect. I want to, this is not very testable. Like, let's start there. I have no way to test some of these things. And so by creating an abstracted interface around these things and putting them in modules, I can test them separately, and more importantly, test the interactions for things like what happens if, you know, some call to turning on the Wi-Fi fails. Well, I can mock out a failed call and then see how my code handles it and write tests and things around that. And so that's what we will be doing. I'm not sure which piece of this I'll tackle first. As a heads up, I am on vacation with the family next week. And when I do that, I try to disconnect, if that makes sense. So I'm out next week because I'll be spending time with the family, not working. And so I'll probably be back. What is that? The week of the April 12th time frame. I should be back to streaming. You'll probably see me pop into the Discord and stuff though between now and then. But just stream wise, this is probably the last stream for the next week or so. So again, I want to thank everybody that has watched. Rogue Security Sparky, thank you for joining. It's always great to have you. Again, for anybody that's watching this after the fact, if you are not in the Discord, you're missing out. A lot of cool stuff happening there, good community interaction. And then again, we're getting some great knowledge dropped in there from Igor from Espressive has been awesome so far as well. So Rogue Security, really appreciate that. That's going to do it for the stream today. I hope everybody has an amazing rest of their day. Have an amazing week. And I will see everybody in about a week from now. Thanks and have a great one.